Verma, Professor Mechanical Engineering Department, Noida Institute of Engineering and Technology, Greater Noida. Today I will be talking about the heat treatment part 3. This will be consisting of the allotropic forms of iron, iron carbon equilibrium diagram, time temperature transformation curve and nucleation and growth of pearlite. So, basically iron carbon equilibrium diagram and the time temperature transformation curve, these two are very important in the material science to understand how the heat treatment is going to take place for the plain carbon steel having various percentages of carbon. Before we start the iron carbon equilibrium diagram, it is equally important to understand what is the allotropic forms of iron. The iron in this diagram, it has been shown from the liquid state. The melting point of iron is 1539 degrees centigrade from the higher temperature. When we are cooling it, when the temperature reaches to 1539 degrees centigrade, a rest point occurs whereby the latent heat is dissipated and there is no time there is no temperature decrease even though time continues increasing. This portion indicates the material in liquid phase is losing its latent heat. After this point, when the material has turned into completely solid, then fall in temperature occurs, but again a rest point occurs at temperature of 1400 degrees centigrade. If you see the structure here, this is delta iron in BCC. BCC means body centered cubic structure. Further, when it is falling from 1400 degrees centigrade, there is again a rest point occurs whereby the heat energy is bringing some transformation within the material. After that transformation has completed, after that only the fall in temperature starts with respect to time. Here the structure of the iron is FCC, that means face centered cubic. This is referred as gamma iron. When you continue cooling it down and you reach a temperature of 910 degrees centigrade, again one arrest point occurs whereby the heat is being utilized by the material to transform some structure change, and that structure change is the material from FCC, it will convert back to BCC, body centered cubic, which is referred as alpha iron. Here again, when it continues, the temperature is cooling down and from 910 to it has reached 768 degrees centigrade, the material starts gaining the properties of magnetism. That means, from here to here the material is non-magnetic, but when you start cooling it beyond this point, up to the room temperature, the material is magnetic. Even though from here to here the iron structure is having body centered cubic. Reverse of this, when you start heating it, you just turn it 180 degree, it will be like this, or you can understand if you start it heating from here from the room temperature, when you continue heating it, you reach a temperature 768 up to which the iron is having the magnetic characteristics. But when you continue heating it, the heat is getting into the material to bring some change, whereby the material will turn from magnetic to non-magnetic, even though the crystal structure will remain same, body centered cubic, and this is referred as alpha iron. So, at this arrest point, when you continue supplying the heat, after that, after when this transformation has occurred from magnetic to non-magnetic, after that only the rise in temperature will continue and will reach up to 910 degrees centigrade. After 910, again arrest point occurs whereby the change in temperature is not there with respect to time, heat supplied is continued. That means, energy is getting into the material to bring some change, and that change is the alpha iron converts into gamma iron, which has got the FCC, face centered cubic structure. When you continue heating it from 910 degrees centigrade to 1400 degrees centigrade, this remains FCC, but beyond 1400, when you continue heating it, heat is getting into the material to bring some change, and that change is the FCC getting converted into BCC. When this transformation from FCC to BCC has completed, then again rise in temperature will continue, and it continues up to melting point 1539 degree centigrade. This is referred as delta iron. Delta iron and alpha iron both are having BCC structure, but there is a change in lattice parameter, because here delta iron it is at higher temperature. So, it has got the lattice parameter slightly higher than the alpha iron, which is also BCC. So, this is the allotropic form of the iron. This is very important. When you carry out the heat treatment, you will be heating it, and the steel which contains mainly iron will be changing its structure from BCC to FCC and like that. Basically, plain carbon steel, it is alloy of carbon and iron. So, carbon size is very small and iron size is very large. So, you find the carbon is getting settled into the space between the large size atoms of iron, and this is referred as interstitial arrangement. Interstitial, this is substitutional. Substitutional means parent atom is replaced by some other alloying element. In case of plain carbon steel, this is not substitutional, this is interstitial, that is to be understood. So, you can see here the carbon atom, it is very small, it has got a atomic radius of 0.7 angstrom, comparing to iron, it is very small in size. Regarding the iron carbon equilibrium diagram. So, the diagram, this contains on the y axis temperature and on the x axis it is percentage carbon. Iron carbon diagram very complicated, it has got various informations, and for the undergraduate students the minimum requirement which I will be telling about today, that I will be explaining about. So, let me start with this sorry. This iron carbon equilibrium diagram, this is very important, and it gives information about the heat treatment which is being carried out on the carbon steel. To start with this, on the x axis we have got the carbon content, carbon percentage. On the y axis we have got the temperature, this is in degree centigrade, and the percentage carbon. So, you start from the 0 and up to certain percentage of carbon. When the percentage of carbon is increasing, you get mild steel. Mild steel means percentage of carbon is very less. You can see here it is 0.025 and slightly higher than that, it is around 0.05. After that, when the carbon percentage continue increasing, the mild steel, next is medium carbon steel. Again further, when the percentage of carbon is increasing, then you get the high carbon steel and very high carbon steel. So, very high carbon steel is up to approximate percentage of 2% of the carbon. Beyond that, the higher percentage of carbon up to 6.5% we refer, this is cast iron. So, starting from here, this is plain carbon steel, and beyond this it is cast iron. Here again further you will get the point where the critical percentage of carbon is 0.83, 0.83 percentage of carbon and less. The steel is referred as hypoeutectoid steel, and the steel having carbon percentage 0.83 and higher will be referred as hypereutectoid steel. On this iron carbon equilibrium diagram, various temperature ranges are there and various regions are there, that will be indicating what is the microstructure of the steel. When you start on the y axis, you get a small triangle type, and the area in between, this will be indicating the alpha iron. Alpha iron is nothing but very small amount of carbon is dissolved into it, and this is a mechanical mixture of carbon and iron. This is referred as alpha ferrite. This line, red color line from here to this red color line from here to here, this will be indicating the upper critical temperature, and this horizontal line will be indicating the lower critical temperature. On the top side at 1539 degree centigrade and beyond, the material is in liquid state. As you know, the percentage of carbon here it is 0, it is pure iron and having the melting point as 1539 degree centigrade. As the percentage of carbon is increasing, you find the drop in melting point and it reaches to a minimum value. It is somewhere 1130 degree centigrade for a percentage of carbon approximately 4.3%. This point is referred here eutectic point. Eutectic point is the point whereby an alloy has got a minimum melting point, because the alloying elements they try to lower the melting point of each other. So, here even though the iron it has got a melting point of 1539, but when it is alloyed with iron when it is alloyed with carbon and the carbon percentage is 4.3, you get a lowest melting point, but when the carbon percentage continue increasing beyond 4.3, again you find there is a rise in melting point. So, minimum melting point occurs here 1130 degree centigrade and this point here it is referred as eutectic point. So, at the eutectic point you will get another reaction whereby beyond this it is in liquid phase and lower than this the liquid phase will turn into simultaneously two solid phases. So, at the eutectic reaction we will be seeing in the next slides. This point here is referred as eutectoid. What do you mean by eutectoid? Eutectoid is the point or it is a critical percentage of carbon in this alloy at certain temperature, whereby one solid will transform into two different solids on cooling or on heating. So, let us say in this region the material available is austenite stake. This austenite at this point, let us say this is the vertical line. So, you continue from here, here everywhere in all this region this is completely austenite, but when the austenite is being cooled you reach at this point and continue cooling further. This austenite being a single solid phase, this will convert into two different solid phases. This side to my left side this will be pearlite and ferrite, but beyond this will be pearlite and cementite. Both are two different solid phases, but above this it is single solid phase austenite. This point whereby on cooling or heating one solid phase converts into two different solid phases, this will be referred as eutectoid point. Another important point here is peritectic. You can see here a small triangle whereby the microstructure here of delta iron, it is delta iron here. Over this it is delta iron plus liquid, because this is the liquidous line, and liquidous line means beyond this to the upper side the material is available in liquid phase, but as you continue cooling it downward, when you reach on the liquidous line the solidification starts, and when this solidification has started it will be completing over a range because it is being alloy. So, over the lower side this line will indicate solidus curve, this line will indicate solidus curve, this line will be indicating liquidus curve. These two are meeting here, that has been referred eutectic point, right. So, this is the small region where the steel is available and this will be referred as delta iron. Over this triangle this will be delta plus L, L means liquid phase, delta means solid phase, delta iron solid phase and liquid phase. So, in this small triangle the material available as mixture of solid phase and liquid phase. Lower side this will be mixture of delta plus gamma, that means in this small region the material is available as mixture of delta iron and gamma iron. When you cool it down beyond this, you reach in this region, this completely has austenitic structure, that means complete it is austenite. between this solidus line and the liquidus line, it is mixture of austenite plus liquid phase, gamma plus L. Similarly, here it is liquid phase plus iron carbide Fe3C. So, let us talk about the hypoeutectoid steel. Hypoeutectoid steel is the steel which contains carbon percentage of less than 0.83. Hypereutectoid steel consists of carbon percentage more than 0.83. In this region, this line, horizontal line, this is referred as lower critical temperature, and this curve is referred as upper critical temperature. This is also referred as A3 line, or this is also referred as ACM. That is the representation. Earlier times they used to say it is ACM. Otherwise, simply you can remember this is the upper critical temperature. This is upper critical temperature in case of hypereutectoid steel, and this is upper critical temperature in case of hypoeutectoid steel. This temperature is very important, 910, because as the carbon percentage is increasing, the eutectoid point, you can see it is reaching here, and the temperature here is 723 degree centigrade, and the steel is having a percentage carbon of 0.83. Equally, this point is very important. Here the carbon percentage is very precisely 2.11%. Very precisely here the carbon percentage is 4.3%. So, we have to remember on this iron carbon diagram where is the liquid phase of material, what is the melting point, what are the various important points which are to be remembered. This is the point corresponding to eutectic point. This temperature is 1130 degree centigrade. This first point 723, next point 910 degree centigrade. These are the equally important points you have to remember as far as the temperature on the y axis is concerned. On the x axis, we have to got the percentage carbon. According to the percentage of carbon, this will be as mild steel, medium carbon, high carbon steel, or very high carbon steel, or beyond that it is cast iron. We consider the carbon percentage only up to 6.5%. Beyond that we do not consider for the iron carbon percentage, because beyond that it is of not very significant as far as the utilization of the iron carbon equilibrium diagram is concerned. Another information here, that up to this region percentage of carbon, the equipments being manufactured of this steel, they are being used for high quality silverware. Slightly increasing the carbon percentage, the equipments manufactured for this are being used for the cutlery. Beyond that, the equipments are being used for the surgical equipment like razor blades. What is the reason that we are reaching here and we are utilizing razor blades material? The reason is that as the percentage of carbon increases, the high hardness occurs, so the material can be utilized for cutting purpose. Secondly, by carrying out the heat treatment, we can have a fine grain structure, and when the fine grain structure of material is there, then a very sharp edge can be produced on the component, so that easy of cutting. As you can understand, the sharpness of the tool determines how efficiently it will be cutting into the material. These are the parts of iron carbon equilibrium diagram. Partly you can see this process. We want to know at various points the microstructure is austenite. How does it look like? You can see the austenite structure here. The austenite grains are there, and the two grains are separated by the grain boundaries. In this region, as I said, the material is in austenite state, and this is the complete 100% austenite. So, you can see the complete austenite grains are there. But as you continue moving downward, that means cooling the material, when you reach at this stage, at the grain boundaries, the ferrite formation occurs. You can see here the small dots are there. So, this is nothing but at the grain boundaries of austenite, ferrite formation continues, and as the temperature continues moving downward, this grows. and ultimately you get another structure which is referred as pearlite. Pearlite is having lamellar structure, ferrite and cementite in alternate layers. We will be seeing this growth in the subsequent slides. So, you can see here the percentage of carbon is constant, but with difference in temperature the microstructure is different. The microstructure here for the same percentage of carbon austenite, but here in this region this is pearlite. This is another region shown here in between for the hypoeutectoid steel, the growth of pearlite. This is for the hypereutectoid steel, the steel which contains the carbon percentage of more than 0.83%. The similarly process, let us draw a vertical line. So, when you are here in the austenite region, then the microstructure is completely austenite, austenite grains are there you can see, but as you continue cooling the material, the formation at the grain boundaries occurs and you get the another structure, that is pearlite. So, here the red color is shown Fe3C, iron carbide. Three important reactions they are occurring in the iron carbon equilibrium diagram at the important points. The first one I said, horizontal line at 723 degrees centigrade where the eutectoid reaction takes place. That means, one solid phase will be converting into two different solid phases. Here the one solid phase is austenite, let us say we are moving in this direction on cooling. So, this will be having the two solid phases, that means ferrite and cementite. When you rise on the upper side, the second horizontal line is at 1130 degree centigrade where eutectic reaction takes place. That means, liquid is changing into solid phase of austenite and solid phase of cementite. I come back to this diagram again. This is the eutectic point, the liquid phase is available here, and when you cool it down, this is getting liquid phase is getting converted into two different solid phases. Liquid phase converting into two different solid phases. When you move still higher for the temperature, the horizontal line at 1490 degree centigrade, that point is referred as peritectic, and the peritectic reaction takes place whereby the liquid plus delta, that means liquid phase plus solid phase on cooling getting converted into single solid phase. So, this reaction is referred as peritectic reaction. This peritectic reaction, that point I have shown there, peritectic point. So, similarly three very important points, eutectic point, eutectoid, eutectic point, eutectoid point and peritectic point. On these points, these are referred as the reactions. Reactions means how the different phases are transforming on cooling or heating into different phases. This is again you can make a comparison here. You can see this is 100% austenite, 100% austenite, 100% austenite. But as you continue in the different percentage of carbon regions, this is 0.4%, 0.8% and 1.2%. So, if you draw a process, a vertical line at the different points, you want to know what is the microstructure of the material. So, you can see it here, this region falls in the region whereby 100% austenite is there, this region indicates whereby it is a mixture, and this region again indicates it is different mixture, right. Similarly here and similarly in this case. This is very important schematic picture of the formation on growth of pearlite. As you know, pearlite is mixture of or mixture, sorry, it is not mixture, it is the lamellar structure, that means alternate layers of ferrite and cementite. how it starts. Let us say this is the grain boundary. So, initially you will find the nucleation, and after that nucleation is taking in the shape of growth. So, it will continue growing and you get the structure of pearlite. This is again you can have a imagination how the nucleation is taking place somewhere in the grain boundary, and when this nucleation has taken place with respect to time, this will be continue growing. When this continues growing, you get finally a structure which is referred as pearlite. It is referred as pearlite because the microstructure, when you view this in the microscope, it resembles like a mother of pearl, CP, जैसे हम हिंदी में बोलते हैं CP. So, when you have a look and comparison with this, it looks like mother of pearl. So, the name has come pearlite. These are the principal phases of steel and their characteristics, very important. Phase: ferrite, austenite or cementite. Crystal structure, as I explained, ferrite has got the BCC, austenite has got the FCC structure. Cementite, it is compound of iron and iron carbide. Characteristics: ferrite is soft and ductile, it is having magnetic characteristics. Austenite, this is again soft, moderate strength, non-magnetic, but cementite is very hard and brittle. Always remember, the material which are very hard, generally they are brittle. In case of cutting tool material, where we carry out the hardening operation to increase the hardness, hardness is followed with brittleness, but cutting tools, when they are brittle, they will not be able to absorb the shock during the cutting. So, in that case we carry out the heat treatment, that is tempering. So, because of tempering, some of the brittleness is getting removed at the cost of hardness, but brittleness comes down. So, material becomes tough, that means it can be fantastically, it can be used for the cutting purpose. This is another very important diagram, that is time temperature transformation curve. This is also referred as S curve or C curve or Benz curve, because the shape, the first curve you see, it is looking like S curve and the second one is looking like C. So, also it is referred as S curve or C curve. On the y axis we have got the temperature, and on the x axis we have got the time. This time is in seconds and it is on log scale. Log scale means 10 power minus 1, 10 power 0, 10 power 1, 10 power 2, 10 power 3 and like that. So, when you calculate 10 power 7 or 8, the time will be in hours, very long period, maybe in days at the end. So, it is very important to remember, on the x axis the time is in seconds on log scale, on the y axis we have got the temperature. You will see one line here in the triple T diagram, this dotted line, this indicates a temperature of 723 degree centigrade. When the steel is beyond this temperature, it will be 100% austenite. Austenite is stable beyond 723 degree centigrade, but when you cool it down, this austenite structure will start transforming into another structure. How it will be transforming, we will be learning on this time temperature transformation curve, right. So, this region between here and here, it is quite wide, but as you move on the upper side, this gets narrowed, and this region indicates, if you draw a horizontal line here, let us say the line is cutting here, I will be showing in my subsequent slides, the line is cutting here. So, here the austenite transformation starts, continues in this region and finishes at this point. So, this point is also referred as beginning point, and the point on this curve will be referred as finishing point or completion point. In between there is a mean line, this line it indicates 50%, that means transformation has taken place approximately up to 50%, generally it is in the mid portion. Again you will find here two letters MS and MF. MS means martensite formation starts, MF martensite formation finished on the lower side, on the upper side MS, on the lower side MF. When this austenite is getting converted as according to the rate of cooling, you will be getting another structure, that is pearlite. On the upper side, if you reach, you will be getting coarse pearlite, and to the lower side you will be getting fine pearlite, and the corresponding temperature is approximately 525 degrees centigrade. When the rate of cooling is reaching here in this region, the austenite will be converting into bainite. Again lower bainite and upper bainite. Upper bainite is also referred as feathery bainite, and lower bainite is also referred as acicular. Its structure I will be showing in the next slides. To the lower side, in case the rate of cooling is very drastic, the austenite will be transforming directly into martensite. So, these two curves in between, only the transformation is taking place. Beyond this, it is referred as incubation period. This is again same curve, but some information is there. This point is referred as nose. Again, as I told, this curve, this indicates the beginning and this indicates the ending. MS, MF, this indicates martensite formation almost 90% completed. In between, martensite formation 50% completed. Over this, M start means martensite formation has started. Martensite structure is very hard and brittle. It has got the body centered tetragonal. The structure is extremely hard. If the austenite is getting converted into martensite, you will get the characteristics of steel to be very hard, having very high strength. Of course, hardness is followed with brittleness. This I said the rate of coolings from here, because as you know, the austenite beyond 723 degrees centigrade, it is stable. So, if you have the austenitic structure which is 723 plus at higher than 723 degrees centigrade, when it has been cooled, this cooling is very drastic. This does not touch the nose of the curve. This is part of the diagram. So, this we want to show what are the different cooling rates. According to the different cooling rates, you will be getting the austenite getting transformed into different structures. Here the cooling rate is drastic. Here it is written water quenching. Water quenching is very fast. The temperature falls down in a fraction of seconds, and the austenite which was 100% here will be transforming into martensite. Martensite formation starts at this point and finishes at this point. Here to here there is no transformation, and this region is referred as incubation period. When the cooling rate is slightly slower than this one, then this is the curve followed. This is referred as oil quenching. In case of water quenching, the heat extraction is very fast. In case of oil quenching, it is somewhat retarded. So, this cooling curve will be cutting this curve. That means, your transformation starts from this point, at this point. From this point to here, there is no transformation, austenite remains austenite up to this point. Again I say this point is referred as incubation period. From here the transformation has started. That means, austenite will be getting converted into, in this region, this will be somewhat fine pearlite and martensite. This you can see here. This results in martensite plus P. P is pearlite. This is written here M martensite, P pearlite. Sorry. On the further slower cooling, the cooling rate is represented here. Generally, this cooling rate is referred in normalizing. So, in case of normalizing, this cooling curve is cutting the S curve here and the C curve here. That means, transformation is taking place from here. Transformation is taking place starting at this point and finishing at this point, and this region lies generally in the range of pearlite, coarse pearlite. coarse pearlite, of course here it has been shown fine pearlite, the temperature range is, yeah, it is around 500. So, it is fine pearlite, but in case of this full annealing where the rate of cooling is bit slower. Again, when the rate of cooling is slower than water quenching, we reach to oil quenched. In case of oil quenched, the structure austenite is transforming into martensite plus pearlite. On still slower cooling, which is referred as normalizing, this is the rate of cooling which is generally followed during the normalizing operation, where the austenite is getting converted into fine pearlite. This is the region indicated in the range where the pearlite is formed. Pearlite means it is again on the upper side coarse pearlite, to the lower side fine pearlite. Still for the slower cooling rate which has been followed in case of full annealing, the austenite is getting transformed into coarse pearlite. So, in case of full annealing, the austenite will be getting converted into coarse pearlite. This graph has been taken for eutectoid steel, which generally contains the carbon percentage of 0.8%. This is more precisely indicates how the transformation is taking place. This is part of the triple T diagram. You can see here from 727 degrees centigrade the cooling has started. We reach the drop in temperature continues up to point B, from A to B drastically, but at point B to D it is isothermal transformation. Isothermal transformation means no further cooling, it is taking place at constant temperature. So, it is a horizontal line with respect to temperature, with respect to time. On the x axis we have got the time. So, time is passing, but there is no drop in temperature. So, when you reach at this point, the transformation begins at point C. The structure which was before C, it was austenite, but it started getting transformed into different structure, and in between here you can see the structure is having austenite and pearlite, but here it is again you can see coarse pearlite, because at point D the transformation has completed and the complete austenite has been converted into this structure. This serration type line, it indicates the transformation process is occurring. Again I repeat, from A, B, C, A to C there is no transformation taking place, and A to C is referred as incubation period. C to D the transformation continues occurring, at point D the transformation is finished, completed. How the pearlite microstructure looks like? This is like this. You can see the light phase is alpha ferrite and the dark phase is Fe3C iron carbide. So, these are the layers, lamellar structure. You can see this is the microstructure and it is also showing the scale. So, this distance is approximately 20 micron. This is again same coarse pearlite and fine pearlite. The magnification here is approximately 3000. This is again at a very large scale, transmission electron micrograph, extremely fine pearlite, it looks like this. This is just for your information, you want to know how does it look like at a higher magnification. This is bainite. Bainite again having the bainite formed at 348 degree centigrade and it looks like this. This is feather type and acicular. Acicular means it is having the needle like structure. These are the again various process, even though I explained. So, let us say this red color process 1, process 1, 2, 3, 4, 4 processes are there on this triple T diagram. They will be indicating how the changes are taking place. Let us take process 1 which is represented by red color line. So, the temperature here is beyond 723 degree centigrade, drastic quenching, and the temperature is dropped around up to 160 degree centigrade. From that, isothermal transformation starts. From here to here, when the MS line is cut, then only the austenite will start transforming into martensite, and this continues transforming at isothermally. Isothermally means temperature is constant. Take the process 2, this is again drastic cooling, but temperature is up to 250 degree centigrade. After 250 it is isothermal transformation. So, here again quenching is taking place and the transformation starts from here and continued. The austenite is getting transformed into martensite. Take the process 3, which is represented by blue color, again drastic quenching up to temperature 300 degree centigrade from the beyond 723 degree centigrade, and at this 300 degree centigrade, when the temperature has been reduced, isothermal transformation starts, means further drop in temperature is arrested. This is isothermal process is taking place and the transformation will start at this point. From here this continues up to here, and when the time has reached that, again quenching has taken place. So, austenite will get transformed into bainite and martensite. Bainite means during this region and martensite means during this region. So, austenite will be getting converted into bainite and martensite. Take the fourth process, which is represented by this color. From the beyond the 723 degree centigrade, sudden quenching is taking place and temperature is approximately 600 degree centigrade. Beyond that, further fall in temperature is arrested and the process is isothermal. That means, austenite up to here remains 100% austenite, but as the curve is touching here and continues, the austenite starts transforming into another structure, fine pearlite. This is isothermal transformation starting here and finishing here. That means, austenite is getting converted totally into pearlite, fine pearlite. When this curve has been reached, beyond that there is no transformation, because transformation has completed here and it started here. That means, in case of process from here to here incubation period, from here to here it is transformation starting, finishing. After that there is no change in its microstructure and completely austenite has been transformed into fine pearlite. So, these are the 4 processes which will indicate how the time temperature transformation curve is being used in the heat treatment. With this I finish. Thank you.